Some elements in the universe are born with a death sentence. They exist only after violent explosions, or inside nuclear reactors, and then they decay away. A quiet billion-year-old star is not supposed to keep them. Yet deep in the constellation Centaurus, the light of HD 1065 carries spectral signatures linked to short-lived nuclear isotopes. If this data is a measurement error, then we are misreading the fundamental language of starlight. If it is real, then nuclear physics is operating where stellar evolution says it cannot. This investigation is not about aliens. It is about a forensic anomaly that tests the limits of nuclear physics and stellar evolution. So what is really happening inside Przybylski's star? To answer that question, astronomers usually look for dramatic anomalies. In the catalog of cosmic anomalies, Tabitha's star KIC 8462852 often dominates the conversation. Its erratic dips in brightness sparked wild theories of alien megastructures, only to be settled most likely by the mundane physics of cosmic dust. But while Tabitha's star is strange because of what blocks its light, HD 101065, better known as Przybylski's star, is strange because of the light itself. Located approximately 357 light-years away in the constellation Centaurus, this object defies the standard census of the galaxy. For the vast majority of the main sequence stars are chemically predictable, a massive reservoir of hydrogen and helium, seasoned with trace amounts of heavier elements like carbon, oxygen, and iron. They follow a strict recipe. Przybylski's star refuses to follow that recipe. It is a calibration anomaly, a single data point that deviates so aggressively from the standard model that it forces us to question our instruments. It contains elements that should not be abundant, and it lacks elements that are supposed to be fundamental. This is not a standard astronomical survey. It is a forensic audit of a physical impossibility. To understand why this star has been quietly unnerving astrophysicists for decades, we must first return to the initial site survey in 1961, where the confusion began not with a wild theory, but with a single baffling observation. The investigation began in 1961 at the Mount Stromlo Observatory in Australia. Polish-Australian astronomer Antoni Przybylski was conducting a routine survey of stars that by all accounts should have been unremarkable. He turned his attention to HD 101065, a star catalogued as a standard magnitude 8 object, too faint to be seen with the naked eye, but bright enough for spectroscopic study. When Przybylski developed the photographic plates, however, the resulting spectrum did not make sense. In stellar spectroscopy, A-type stars that are hotter than our sun and typically more massive, typically display a predictable signature strong absorption lines of hydrogen and ionized metals, like calcium or magnesium. But the light from HD 101065 was a mess of unrecognizable signals. The hydrogen lines were strangely weak, and the familiar fingerprints of iron, the standard yardstick for stellar metallicity, were virtually absent. Initial interpretations were contradictory. Przybylski first hypothesized that the star was metal-poor, a relic from an ancient generation of stars formed before the universe was enriched with heavy elements. Yet this conclusion clashed with the sheer density of other absorption lines crowding the spectrum. The star wasn't empty. It was full of the wrong things. It took years of debate to reclassify HD 101065 as an app star, a peculiar A-type. But even within this island of misfit stars, Przybylski's discovery was an extreme outlier. It defied the standard classification models so thoroughly that astronomers struggled to determine its temperature or its true composition. It was a chaotic signal in a field that relies on order. But as modern astrophysics would later reveal, the chaos in the data was an illusion. The spectrum was actually incredibly precise, too precise. Przybylski didn't find a weird star. He found a spectrum that refused to fit any template. And the reason might be physical, not chemical. Before we can interrogate the elements inside the star, we need to understand the laboratory they live in. Because this star's atmosphere is unusually stable. Most A-type stars are rapidly rotating objects. They typically rotate at speeds exceeding 100 kilometers per second. From an observational standpoint, this speed is a problem. Rapid rotation causes one side of the star to move away from us, while the other moves towards us, creating a Doppler effect that smears out the sharp spectral lines into wide, blurry troughs. This Doppler broadening effectively erases the fine details of the star's chemical fingerprint. HD 101065 does not have this problem. Observations of its magnetic field variations suggest that this star is rotating with agonizing slowness. While a typical star might complete a rotation in a day or two, estimates for Przybylski's star range from decades to potentially centuries for a single revolution. In the context of stellar dynamics, it is effectively standing still. This lack of rotational turbulence is the first crucial clue. But there is a second force at work here: magnetism. The star possesses a magnetic field strength measured at approximately 2,500 gauss, equivalent to about 2.5 kilogauss, thousands of times stronger than the Earth's magnetic field, and unusually intense for an A-type star. In a standard star like our Sun, the outer layers are dominated by convection, the boiling, churning motion of hot plasma rising and falling. This mixing process keeps the atmosphere homogenized, ensuring that the surface composition roughly matches the interior. However, in HD 101065, the intense magnetic field acts as a stagnant laboratory. The magnetic lines of force constitute a rigid cage that suppresses these convective currents. It locks the plasma in place, preventing the interior material from mixing with the surface. This creates a unique physical environment, a star that is both rotationally frozen and magnetically stabilized. It behaves like a dynamically sealed system. The surface of Przybylski's star is not a churning ocean of plasma. It is a calm, stratified lake. And it is this unnatural stillness that sets the stage for the chemical impossibility that follows. A slow magnetized star creates a quiet atmosphere, quiet enough for chemistry to stratify, like layers in a sealed container. Now we can read the evidence, because spectroscopy isn't just looking at light, it's fingerprinting matter. When light from a star's core passes through its cooler outer atmosphere, the atoms suspended in that gas absorb specific wavelengths of energy. These missing wavelengths appear as dark gaps in the rainbow of the spectrum known as absorption lines. Each chemical element has a unique configuration of electrons, meaning it absorbs a unique set of frequencies. To an astrophysicist, these lines are as definitive as a barcode scan. In the vast majority of stars, this barcode is dominated by iron. Iron is the cosmic standard, the endpoint of energy-producing stellar fusion in massive stars, and its strong spectral lines usually serve as the baseline for measuring a star's metallicity. But in HD 101065, the iron lines are surprisingly faint, initially leading astronomers to believe the star had a significant iron deficiency, perhaps containing iron at levels 50 to 60 times lower than in our own Sun. However, where the iron lines should have been, the spectrum was choked with something else. Przybylski and later researchers using higher resolution instruments found the signature of the lanthanides. These are the rare earth elements on the periodic table: lanthanum, cerium, praseodymium, neodymium. While they are called rare, they are not actually scarce in the universe. They are just difficult to separate. Yet in this star, they were appearing with abundances that were statistically incompatible with a normal stellar composition. Some measurements suggested these elements were present at levels 10,000 times higher than in the Sun. The sheer density of these spectral lines is what makes HD 101065 so difficult to study. The forest of absorption lines is so thick that it becomes difficult to find the continuum of light behind them. The star is effectively draped in a heavy cloak of exotic metals. For decades, this chemical inversion, iron sinking, rare earths rising, was the defining mystery of Przybylski's star. But this is not a violation of physics. It is the result of a specific, elegant mechanism that turns the star into a natural sorting system. To understand how a star can separate its elements so cleanly, we must look at the invisible tug-of-war happening in its atmosphere. This is the mechanism of radiative levitation. In a turbulent star like the Sun, mixing currents churn everything together. But remember, HD 101065 is magnetically stabilized and rotationally slow. Its atmosphere is a stagnant, quiet pond. In this stillness, two forces compete for control over every single atom. The first force is gravity, which pulls atoms down toward the core. Since heavy elements have more mass, our intuition suggests they should sink. The second force is radiation pressure. the photons streaming outward from the hot core, carry momentum. When a photon strikes an atom, it transfers that momentum, pushing the atom outward like wind hitting a sail. This is where the star acts as an optical centrifuge. This centrifuge does not sort atoms by mass. It sorts them by their opacity, their ability to catch light. An atom like iron in the specific temperature conditions of this star has a relatively small cross-section for absorption. It is aerodynamically sleek to the photon wind. As a result, gravity wins the tug of war. The iron atoms drift downward, sinking out of sight into the deeper layers of the star. This explains why the surface appears iron-poor. The iron is still there, just hidden in the depths. The lanthanides, however, are different. They have complex electron structures with many available energy states. To the stream of outgoing photons, a lanthanide atom is like a massive parachute. It absorbs energy across thousands of different wavelengths. The radiation pressure generated by this bombardment is tremendous, strong enough to overcome the pull of gravity. The photons physically lift these heavy atoms within the stellar envelope and suspend them in the upper atmosphere. What we are seeing is not the star's true composition, but a levitated skin, a concentrated layer of rare earth elements, floating on top of the star, supported solely by the pressure of light. This phenomenon, known as abundant stratification, is a known behavior in apstars. It would be a textbook example of diffusion theory in a magnetic atmosphere. But the investigation did not stop with the rare earths. As spectral resolution improved, astronomers began to look closer at the noise in the data. They began to look for heavier things. If the optical centrifuge can lift lanthanides, could it lift something else? In 2008, a team led by Vera Gopka pushed this forensic audit into dangerous territory. They claimed to find lines that did not belong to stable elements like neodymium or praseodymium. They found lines that belonged to the ghosts of the periodic table. If this were the whole story, rare earths floating up iron sinking down HD 101065 would be peculiar but explainable. Then 2008 happened. Gopka's spectrum didn't just show odd chemistry. It allegedly showed elements that shouldn't survive long enough to be seen at all. In 2008, a team led by Vera Gopka from the main astronomical observatory in Kiev published a paper that, if correct, would challenge the foundations of stellar astrophysics. While analyzing high-resolution spectra of HD 101065, they moved beyond the lanthanides and began searching for the actinides, the heavy radioactive row at the bottom of the periodic table. What they claimed to find was a roster of nuclear heavyweights: actinium, protactinium, neptunium, plutonium, americium, curium, berkelium, californium, and einsteinium. To understand the gravity of this claim, we must focus on the heaviest element on that list, einsteinium element, 99. Einsteinium is not an element that you dig out of the ground. It is not found in asteroids. It is not found in the Earth's crust, and until this claim, it had never been convincingly identified in a natural astrophysical environment. The first time humanity laid eyes on einsteinium was in November 1952 in the fallout debris of Ivy Mike, the first successful detonation of a hydrogen bomb. To create einsteinium, you need to bombard a nucleus with so many neutrons so quickly that it doesn't have time to decay before absorbing the next one. This requires the neutron flux of a thermonuclear explosion or a specialized high-flux nuclear reactor. It is a synthetic element produced only under extraordinarily energetic conditions. Yet the spectral analysis of HD 101065 identified specific absorption wavelengths that match the theoretical signature of einsteinium. If this identification is correct, then a quiet, stable star in the Centaurus constellation is somehow exhibiting spectral signatures of a material that on Earth exists only as a fleeting byproduct of our most destructive weapons. But the presence of a synthetic element is only half of the problem. The real smoking gun isn't the identity of the element. It is the time it takes to die. This brings us to the core of the paradox, the half-life conflict. Every radioactive isotope has a clock attached to it. This is its half-life, the time it takes for 50% of the material to decay into something else. These clocks are immutable laws of physics. They do not stop, and they do not slow down. HD 101065 is an old star. Based on its motion through the galaxy and its stellar association, it is estimated to be over 1 billion years old. In the timescale of the universe, this is a mature object. Now, let's look at the clocks of the elements reported in its atmosphere. Plutonium-239 half-life of 24,000 years. Actinium-227 half-life of 21.77 years. Einsteinium-253 half-life of 20.47 days. This creates a massive forensic contradiction. If these elements were formed when the star was born a billion years ago, they should have decayed into much lighter stable elements eons ago. There should not be a single atom left to absorb light today. Finding Einsteinium-253 in this star is equivalent to opening an Egyptian tomb sealed 3,000 years ago and finding a cup of coffee that is still hot. Physics dictates that these elements cannot be primordial. They cannot be leftovers from the star's birth. Even the mechanism of radiative levitation, our optical centrifuge, cannot solve this. Levitation can lift heavy elements to the surface, but it cannot stop them from decaying. If you levitate a block of ice into the sky, it will still melt. If you levitate Einsteinium, it will still vanish in a matter of weeks. Therefore, the presence of these lines represents time-critical evidence. In nuclear forensics, when you see a short-lived isotope, it implies a state of secular equilibrium. This means the rate of decay is continuously balanced by the rate of creation, or by an ongoing external supply. For the coffee to be hot in the tomb, someone must be pouring fresh coffee into the cup right now. For Einsteinium to be visible in the spectrum of HD 10.1065 today, one of two things must be true. There must be an active process, natural or otherwise, continuously supplying these isotopes, continuously manufacturing and replenishing these elements as fast as they decay. Or the entire forensic analysis is flawed. A 20-day isotope in a billion-year star is not unusual. It's time-critical evidence, which leaves only two options: the ID is wrong, or something is supplying it. So we do what any forensic audit does next. We test the measurement before we accuse reality. Before we rewrite the textbooks on stellar evolution, we must address the false positive scenario. The claim of finding Einsteinium relies on a fragile chain of evidence that has several weak links. The primary risk is misidentification. Spectroscopy is about matching patterns. We observe dark lines in the star's light and match them to known reference spectra, measured in laboratories on Earth. But because Einsteinium is so radioactive and rare, we have never put a sample of it in a 6,000-degree furnace to measure its spectrum experimentally. The lines we are looking for are based on quantum mechanical calculations, theoretical predictions of where the lines should be. If the theory is off by even a fraction of a nanometer, the match is invalid. Furthermore, we must remember the lanthanide forest. The atmosphere of HD 10.1065 is so crowded with thousands of absorption lines from rare earth elements, such as neodymium and praseodymium, that they overlap and blend together. It is possible that what looks like an Einsteinium line is actually a coincidental cluster of three different neodymium lines blurring together. This is spectral contamination. However, Gopka's team argued that they found not just one line, but multiple matching lines for these radioactive elements, increasing the statistical probability that the signal is real. And importantly, other researchers haven't definitively debunked it. They've largely ignored it, because it is too difficult to verify without better lab data. But this leaves us in an uncomfortable position. If the identification is wrong, it's a cautionary tale about data noise. But if it is right, even partially, then we are looking at a star that is essentially a nuclear factory. If nature is doing this, how? And if nature isn't doing this, who is? If we accept the spectral data as accurate, we must find a mechanism capable of generating these isotopes. If nature can manufacture super-heavy nuclei, it rewrites nuclear physics. If it can't, we have to ask a harder question. The leading natural hypothesis suggests that HD 10.1065 is operating as a natural particle accelerator. Standard nuclear physics tells us that naturally occurring long-lived nuclei taper off around uranium. Beyond that, most nuclei are too unstable to persist without continuous production. However, since the 1960s, physicists have long theorized a hypothesized island of stability. The theory posits that if a nucleus can acquire a magic number of neutrons, specifically 184, it might regain stability. These super-heavy elements located far beyond Einsteinium could, in principle, have much longer half-lives than neighboring super-heavy nuclei. In this scenario, Przybylski's star might be one of the rare places in the universe with the right conditions to forge these super-heavy elements, perhaps flerovium element 114 or unbenyllium element 120. What we are seeing in the spectrum, the Einsteinium, the plutonium, the actinium, are not the primary creation. They are the decay products. They are the radioactive ash falling from the island of stability, as those super-heavy giants slowly break apart. If this is true, HD 101065 is the holy grail of nuclear physics, a visible proof that the island of stability exists. But this explanation has a flaw. We have never seen these elements in supernova remnants or neutron star collisions events far more violent than a quiet A-type star. Why would the universe hide its most exotic creation in such a mundane location? This brings us to the most controversial possibility. This is the speculative box clearly labeled. Not aliens in the sci-fi sense, but a logistics problem. Could a civilization pollute a star on purpose? In 1966, Carl Sagan and Joseph Shklovsky proposed that an advanced civilization might deliberately salt their star to attract attention. Later, astrophysicists Whitmire and Wright refined this into a darker, more pragmatic hypothesis: cosmic fly tipping. Imagine a civilization that has mastered high-energy physics operating at what is known as Type 2 on the Kardashev scale. Their industrial processes might generate colossal amounts of radioactive waste byproducts that are too dangerous to keep on a planet. Where do you dump billions of tons of Einsteinium and plutonium? You dump it in the incinerator. In this simulation, the star is not a beacon. It is a landfill. The civilization orchestrates a continuous supply chain, dropping packets of radioactive isotopes into the star. Because of the star's intense magnetic field and lack of convection, a condition often described as a stagnant laboratory, this waste does not sink immediately. It gets trapped in the upper atmosphere, floating there just long enough to be detected by our telescopes before decaying or drifting down. To match the abundances we see in HD 101065, the logistics are staggering. Calculations suggest they would need to dump a mass of material roughly equivalent to a significant asteroid comparable to Vesta every single year. Science anchor. This scenario is thermodynamically conceivable. A star is an excellent heat sink for entropy disposal. However, it remains evidentially weak unless it predicts additional testable signatures, such as specific orbital debris fields or infrared waste heat that matches this industrial scale. We have a natural suspect that defies standard astrophysics, the island hypothesis, and an artificial suspect that defies probability, the salting scenario. To solve this, we do not need more speculation, we need a stricter audit. We know exactly how to test this. The fact that this case remains cold is a choice, not a necessity. A forensic audit plan would require 3 steps. First, reobservation. We need to point modern high-resolution spectrographs, especially southern facilities such as UVES or Espresso, at HD 101065 to confirm whether the actinide lines are truly present or merely ghosts created by data noise. Second, laboratory cross-reference. We need better laboratory benchmarks for the relevant actinide lines, either through direct measurements where feasible or through validated calculations anchored to experimental data. We cannot match fingerprints if we do not know what the suspect's fingerprints look like. Third, a stratification check. If these elements are introduced from outside the star through an artificial process, their vertical distribution in the atmosphere may look different than if they are levitated upward by a natural internal mechanism. We know how to check, so why haven't we? Why is a star that potentially harbors nuclear waste or impossible elements not the biggest story in astronomy? The answer lies in the quiet gap between curiosity and career risk. Sometimes the strangest cases don't die because they're solved. They die because they're inconvenient. First, there is the geography of the observation. HD 101065 sits deep in the southern sky, invisible to the great observatories of the northern hemisphere, where much of the world's funding is concentrated. But the bigger barrier is the fear of a modern gaps accusation, of being seen as invoking unknowns where mechanisms are unclear. In modern science, extraordinary claims require extraordinary evidence. To publish a paper confirming Einsteinium in a star is to invite intense scrutiny. If you are wrong, it is a career-ending error of spectral misidentification. If you are right, you are accused of invoking aliens or fringe physics. For most researchers, it is safer to study the thousands of stars that fit the model than to bet a reputation on the one that breaks it. As a result, the 2008 claim sits in limbo, neither debunked nor confirmed. It is a sealed file, waiting for a detective brave enough to reopen it. We end this forensic audit not with a conviction, but with an open warrant. HD 101065 remains among the most chemically peculiar stars known. Whether it is a natural particle accelerator revealing the island of stability, a cosmic landfill for a silent civilization, or simply a humbling reminder of how easily complex data can deceive us, it serves a purpose. It forces us to look at the periodic table of the stars and admit that some pages are still missing. The universe is under no obligation to make sense to us, but we are under an obligation to keep looking until it does. When we finally reobserve HD 101065 with modern spectra, what signatures do we expect to disappear, and which ones should remain?